Does it ever stop raining on this route? Seriously, you'd think that one of these days the rain would eventually end here, but it just keeps on going and going and going. It's like the Energizer Bunny, I swear. Someone tell me I'm not the only one that remembers that ad campaign. Anyways, it never stops raining on routes 212 and 215 in Brilliant Diamond and Shining Pearl. At least in the original Diamond and Pearl, there was one day it would stop raining on Route 212. But in the remake, nope, it just keeps on raining. This got me thinking, is it possible for one place to have rain every single day of the entire year? Once this question popped into my head, I knew what I needed to do. You probably guessed it if you've been on this channel before. That meteorology brain of mine doesn't seem to like to rest. I needed to solve this mystery as to why it rains on these routes. Now, first things first, we need to ask ourselves a critical question. What causes precipitation to happen in the region of Sinnoh? The best place to start is to look at the region's geography. What features does it contain that are conducive to the development of rain showers? Taking a quick look at the map, we can see that this is an island, given that there's water on all sides and it is not landlocked in any capacity. That and the anime refers to Sinnoh as an island, so I'm going to have to go with Ash Ketchum on this one. This is good news for our purposes, since it means we have ample water to evaporate and condense into rain showers, per the water cycle, of course. If we have more moisture that is available to evaporate and condense into clouds, this means we get more rain showers. However, this would impact the entire island, not just the routes in question. We should see increased precipitation over the entire landmass. But we only see a ton of rain over routes 212 and 215. This can't just be a result of this place being an island. Given this, I took a look at where both routes are located. Luckily, they do happen to sit near the edges of the island, relatively close to the ocean. This could potentially help our case for getting precipitation along these routes, depending on the wind direction, of course. If the wind is going from the north to the south, we're more likely to get precipitation that occurs over Route 215 given its location to the ocean. For Route 212, the wind direction would have to be from the south going to the north for it to receive precipitation from the ocean waters. Sure, this works, but would it work to the point where we'd see rain consistently over the area for days on end? Decidedly not. This rain can last for a while, don't get me wrong, but if the wind direction shifts, that area will no longer receive the rain from the ocean. Unless the wind is 100% consistent, as in it's always blowing in exactly the right direction, then this cannot happen. Wind will usually blow towards the source of the lowest pressure. After all, wind blows in the direction from high to low pressure, always seeking to find its equilibrium. It can't constantly blow in the same direction if the pressure of the atmosphere changes, which it constantly does. So if this doesn't work, are there any other features that could cause rain like this to occur constantly? Well, there is this lovely feature that just so happens to exist on Sinnoh. Most other Pokémon regions across the various games and anime have a mountain or something close to it, but Sinnoh is different from its counterparts. As we've seen in the Generation 4 games, and in Legends Arceus, there's a giant mountain range that runs straight down the middle of the region. Mount Coronet is the tallest peak in all of Sinnoh, with its mountain spreading vertically across the entire continent. This begs the question, how does precipitation occur in a mountainous region? To solve this problem, I went back to one of the first concepts I learned during my days as a student, the mountain problem. No, seriously, that's what we called it. You'll have to pardon the schematic on the mountain problem. I had to draw it myself. I'm not exactly an artist, so this is what I came up with on the fly. You're going to have to forgive the simplicity. Hopefully it doesn't bug too many of you. So the mountain problem goes a little something like this. Say we have a parcel of air. If we want it to rain, we need this parcel to become fully saturated. That's the only way we're getting precipitation. For this to happen, the mountain has to naturally lift the air parcel higher due to the pressure of the atmosphere decreasing as we increase in altitude. But that's not all we need. For the parcel to rise, it needs to be warmer than the surrounding atmosphere. As the parcel ascends up the mountain, the parcel is going to naturally decrease in temperature, since temperature decreases as we increase in altitude. It'll decrease at a relatively quick rate, around 9.8 degrees Celsius per kilometer. The other thing that will decrease with altitude is the dew point temperature. For our purposes, the dew point temperature is the temperature that a body of air must be cooled to in order to be saturated. Now, the dew point temperature will also decrease, but it will do so at a much slower rate than the air temperature of the parcel, anywhere from 1 degrees to 2 degrees Celsius per kilometer. You might be able to see where this is going. Eventually, the temperature of the parcel is going to decrease, as will the dew point temperature, until they are equal to one another. Given that these two temperatures decrease at a different rate, they will become equal to one another at some point on this mountain. Once the parcel is the same temperature as the dew point, it's officially saturated and can no longer hold any moisture. This results in precipitation occurring on that side of the mountain. Theoretically, this parcel can still rise, but it will precipitate a lot less as it rises to the mountain peak, and it will also rise at a slower rate than it did when it was unsaturated. While it rises, the dew point temperature will decrease at the same rate, around 5 degrees Celsius per kilometer, until it dries itself out, becoming unsaturated once more. This usually happens around the mountain peak. Now eventually this parcel has to pass over the mountain peak. It can't just stay there forever, of course. And when it does, it will descend on what we call the leeward side of the mountain, which causes the parcel to increase in temperature. After all, temperature increases as we decrease in altitude. The dew point temperature will also rise on this side of the mountain. However, the air parcel at dew point temperature will not increase at the same rate. We usually don't get rain on the leeward side of the mountain for this reason. The dew point temperature, similar to the windward side of the mountain, will increase at a rate of about 2 degrees Celsius per kilometer. The air parcel, on the other hand, will increase its temperature at a rate of 9.8 degrees Celsius per kilometer, the same as before. Now, I'm pretty sure you don't need me to tell you that 9.8 degrees Celsius per kilometer is quicker than 2 degrees Celsius per kilometer. And if they're both increasing at those rates, temperature and dew point will never be equal, at least not on this side of the mountain. This usually results in the leeward side of the mountain being significantly drier than the windward side of the mountain would be. Keeping this in mind, I took a look at where these routes fall compared to where the mountain range is. Route 212 and 215 are on the same side of the mountain, the eastern side. This presents an interesting conundrum. If we use the northern hemisphere as our basis, air flows from west to east most of the time. For the mountain problem to work for these routes, we need to have airflow from the western side of the mountain to the eastern side of the mountain. This would mean that we'd expect the western side to have the rainy routes in Sinnoh, not the eastern side. So what exactly is going on here? Why would the eastern side of the mountain have continuous rainfall? For this to work, the wind direction would have to be from the east going to the west, the exact opposite of what it is in the northern hemisphere. Then I got to thinking, wait, what if this isn't the northern hemisphere? See, there is one area of Earth that I can think of where air flows from east to west, the southern hemisphere. That may seem strange to some of you, so let me explain. Why does wind flow from east to west in the southern hemisphere, yet from west to east in the northern hemisphere? First, we need to understand exactly how air flows across Earth. Let's start with a hypothetical. If the Earth did not rotate and remain stationary, the atmosphere would circulate between the poles and the equator, going back and forth. Since air flows from high pressure, which in this case is the poles, to a lower pressure, in this case the equator, this would result in a continuous flow between these two regions. However, since the Earth does indeed rotate, this causes the circulating air to be deflected. It's deflected towards the right in the northern hemisphere and towards the left in the southern hemisphere, resulting in curved paths. This is known as the Coriolis effect. As long as we're 5 degrees north or south of the equator, this effect is going to apply across the entire planet. The Coriolis effect likely applies to our scenario here. We can guess that Sinnoh is not directly located on the equator given that it consists of various different climates. Sinnoh has drier regions along with wet regions, as well as areas where it snows constantly. I'm gonna give you a little spoiler alert, it usually doesn't snow in the tropics. It's just a tad too warm for that. Based on this, we can assume we're a bit further away than the tropical regions of the world. Given that the side of the mountain with the most precipitation is east rather than west, we can take a guess that Sinnoh would be located in the southern hemisphere, as air seemingly flows from left to right. Okay, great! We've solved the problem! That means the mountain problem is the reason why we get all this precipitation on these two routes, right? If only that were true. Meteorology tends to come with a lot of complications. Usually friction's my biggest problem. However, this time, we have a different problem. I realized something when I was thinking this up. What is Sinnoh based off of? That's when I ran into the issue. Most regions in the Pokémon series are based off a real-world location. Sinnoh in particular is based off Hokkaido, the northernmost island of Japan. Global geography may not be my strong suit, but I'm pretty sure that Japan is not in the southern hemisphere. I took a quick look as to where Hokkaido is, and I can indeed confirm that the island is decidedly located in the northern hemisphere, not the southern hemisphere. And in the northern hemisphere, air flows from west to east. Assuming this holds true for Sinnoh as well, this can't be the reason why it constantly rains on routes 212 and 215. Now you might be asking yourself, well, what if we ignored this problem and put Sinnoh in the southern hemisphere? Sure, we could do that, why not? Yet, even if we take out this assumption and say it's located in the southern hemisphere, well, even regions with a lot of rain don't get it every single second of every single day of the year. Rain will eventually stop under various circumstances, such as when dry air infiltrates the system, when clouds become unsaturated, when a high-pressure system occurs, among various other circumstances. Meteorologically, to rain every single second of every day would have to be the result of something beyond the typical scope of nature, like a Pokémon using rain dance. Wait a minute. Is that our solution? Is there a Pokémon on these routes that knows the move rain dance? Let's take a quick look. Digging into the Pokemon that can learn Rain Dance via leveling up, it seems that Meryl and Wooper can indeed learn Rain Dance on Route 212. This could mean that rain is occurring due to these Pokemon constantly dancing and forcing rain upon the area. On top of that, on Route 212, you can find a woman that used to run Hoen's Weather Institute that trades TMs for weather-changing effects for sure to find. One of those TMs is the TM for Rain Dance. This might explain why it rains on Route 212 constantly. But what about Route 215? Well, I checked. I looked everywhere. There are no Pokemon that are roaming around in the wild that have this move. No Pokemon you can catch on this route already have Rain Dance either. We also don't have the TM lady here. Is it possible that one of the trainers on Route 215 is constantly spamming Rain Dance? That doesn't seem logical of them to do, and I doubt it, so what gives? Why does it do this? Well, as I've learned in my years of study, if it doesn't make sense meteorologically, and it doesn't make sense lore-wise, I think we know what that means. It's video game logic. Thank you all so much for watching. If you enjoyed the video, be sure to leave a like and subscribe. I will see you all in the next one. Have a good day.